Example 2, we're actually given two separate rounded values, one for P and one for Q. They're both rounded to the nearest 1 centimetre, so that is the rounding. We're then asked in parts A to D to work out the largest or smallest values of various expressions with P and Q. So that means we're going to be working with the upper and lower bounds for P and Q. Now we can't work out their bounds until we work out the error. So error first. Now they're both rounded to the nearest 1 centimetre, so the given rounding is just 1. So to get the error, we're going to divide the given rounding by 2. So that's going to give us 0.5. So that's the error for P and Q. Now also, because there is more than one rounded value, it makes sense to actually draw a table to summarize all the information. So what I'm going to do is draw a table, and we're going to have the two quantities P and Q in our table. So we're going to have what their rounded value is. We're going to work out the error for each of them, which we've just done. And we're going to get the lower bound and the upper bound for each of them. Okay, now let's copy down the rounded values for P and Q. So P is 12 centimetres and Q is 5 centimetres. And we've just worked out the error for each of them. The error is 0.5 centimetres. And now we're going to work out the lower and the upper bounds for each. So let's start with P. To get the lower bound, in other words, the largest possible value that P can actually be, we have to subtract the error from the rounded value. So 12 subtract 0.5 is going to give us 11.5 centimetres. And then to get the upper bound for P, the largest possible value that the actual value for P can be, we add on the error. So 12 plus 0.5 is going to give us 12.5 centimetres. Do the same for Q. So to get the lower bound, the smallest possible value that the actual value of Q could be, we subtract the error from the rounded value. So 5 subtract 0.5 is going to give us 4.5 centimetres. And then to get the upper bound for Q, in other words, the largest value that the actual value of Q could be, we add on the error to the rounded value. So 5 plus 0.5 is going to give us 5.5 centimetres. So now we're going to use the table to help us answer parts A to D. So let's take part A first. Okay, we want the largest value for P plus 2Q. So we want to make this expression as big as possible. Well, the only way we can make it as big as possible is when we take the upper bounds for P and Q. So we're going to sub the upper bounds for P and Q into this expression. So the upper bound for P is 12.5. And then we're adding on 2 times the upper bound for Q. So 12.5 plus 2 times 5.5. Two 5.5s are 11. So 12.5 plus 11 is going to give us 23.5. And that is going to be in centimetres. Okay, let's look at part B. So part B wants us to get the smallest value for P minus Q. Now we need to be careful here. We want to make P minus Q as small as possible. So in order to do that, you want to make P small. You want to make the value of P its lower bound. And then you want to subtract the upper bound for Q, because you want to start with a very small value and subtract a big value from it to make it small overall. So what we're going to do is we're going to use the lower bound for P. The starting value is going to be small. And we're going to use the upper bound for Q. Because what we are subtracting, we want to make it big. So we're going to chuck those in. So the lower bound for P, if we go back to the table, is 11.5. And we're subtracting the upper bound for Q. So we want to subtract 5.5. So that's just going to leave us with 6 centimeters. Okay, part C. We want the largest value for a fraction, Q over P. Now again, think common sense. How do you make a fraction as big as possible? Well, to make it as big as you can, you want the numerator to be big. So what you're starting with in the numerator, you want it to be big. And then what you're dividing it by, you want to make it as small as possible. So something really big divided by something really small overall is going to be big, or is going to be as large as possible. So we're going to use the upper bound for Q, and we're going to use the lower bound for P. Okay, so let's do that. So if we go back to our table, upper bound for Q is 5.5. And we're dividing that by the lower bound for P, which is 11.5. So we've got 5.5 over 11.5. Now we'll type it into our calculator using our fraction button. Now, what I would actually do when I type it in is I would actually just keep it as a fraction here. See the way it turns out to be 11 over 23. If it turned out to be improper, you could turn it into a mixed, but I wouldn't give it as a big stringy decimal. So keep it exact. So it would actually be 11 over 23. Would be our answer there. Okay. Again, in terms of units, you're dividing a length by a length. So actually, there's no real need for units here, to be honest. In fact, we could get away without units for part B and part A because it's just asking us for the value. So it's not really interested in what the units are. So the value for part C is just 11 over 23. Okay, part D, it wants us to get the smallest value of Q over P. Now again, common sense, we want to make this fraction as small as possible. So the starting value on the numerator, you want to make it small to begin with. and then you want to divide it by something really big. So something small divided by something really big overall is going to be as small as possible. So in this situation, we're going to use the lower bound for Q, and we're going to use the upper bound for P. So if we go back to your table then, lower bound for Q is 4.5, and that's being divided by the upper bound for P. So go back to table, upper bound for P is 12.5. And again, we can type it into our calculator using our fraction button, and again the calculator is going to give that as 9 over 25, and it's perfectly fine to leave it like that. I wouldn't hit SD and write it out even as a decimal. I would keep it just as a fraction there. So 9 over 25. Okay, and that's it. So that was a good example where there was more than one rounded value. So when there's more than one rounded value, it's a really good idea to draw out a table, put the two values down and what they are is rounded, work out the error for each and the lower and the upper bounds, and then you can just lift the information from the table to answer each part of the question.